All right, continuing our discussion of basic antiderivatives, or indefinite integrals if you prefer. The inverse hyperbolic sign, what's the derivative of that? Well, I don't think I talked about that one before. Here's how it goes. I might have. Oh no, I can't remember all of a sudden. Oh well. Anyway, here's how you derive it. Take cosh of both sides, differentiate implicitly. Notice that cosh squared minus sinh squared being 1 provides that the square root of x squared minus 1 is equal to sinh y, right? So dy dx is 1 over sinh y, and as we just explained, this is the same as so I have 1 over the square root of x squared minus 1, and there you have it. The derivative of inverse hyperbolic cosine is 1 over the square root of x squared minus 1. Now if you look at this expression, you're going to need what? You're going to need that the absolute value of x, right, is less than 1. Wait a minute. How to say this? Well, this expression would seem to suggest that, right? But as I mentioned to you guys before, to be more careful, I mean, this would seem to suggest that, right? But remember, the domain of inverse hyperbolic cosine is, the way where it makes sense is for x greater than 1. So, I mean, more to the point, the range of cosh, remember what cosh looks like? Looks like this guy, right? So the smallest cosh is 1, and then it's bigger and bigger. So when I take cosh inverse of something, something I take the value of must be in the range of hyperbolic cosine. That's 1 to infinity. So this formula is only good for x greater than 1. All right, anyway, so the integral of dx over the square root of x squared minus 1, as a consequence of this little fun fact, is simply inverse hyperbolic cosine of x plus a constant. Now, part of the reason this is not as well known a fact as the ones we looked at for like inverse sine and inverse tangent is just that, you know, well, inverse hyperbolic cosine is not as well known, I think, amongst the general mathematically inclined public, engineers and so forth. But it is a function that's well defined, and you know, you can look up values of it and such. I mean, there are built-in functions in Mathematica and so forth. Anyway, all right, so that's the one thing. The other thing is, for inverse hyperbolic sine, we can go through the same calculation, and it brings us to the fact that the derivative of inverse hyperbolic sine is 1 over the square root of 1 plus x squared. And from this, we get another basic integral, the integral of dx over the square root of 1 plus x squared is equal to inverse hyperbolic sine of x plus a constant, of course. And that one has no strings attached because, remember, we can take the inverse hyperbolic sine of anything because the range of sinh is everything. It's injective everywhere. It has a global inverse. And reflectively, this formula for the antiderivative, 1 plus x squared, well, that's good for all real x, you know? So one way to, you know, you can, if you wanted to try to memorize these, and I don't know, it might be worthwhile, is that, you know, the formula is reflective of the very different nature of inverse cosh and inverse sinh, right? Inverse sinh making sense for all x versus inverse cosh only making sense for x greater than 1. Okay, anyway, so there's that. Another couple of lesser known integrals, well, in my opinion, lesser known. I suppose if your life work is based around an analysis of some mathematical model which happens to involve inverse hyperbolic sine, you probably know this integral pretty well. But anyway, the derivative of inverse hyperbolic tangent is 1 over the well, it's 1 over 1 minus x squared, so that gives us this kind of cute formula. The integral of dx over 1 minus x squared is just equal to inverse hyperbolic tangent. Now that you got to be careful with because there's strings attached here. There's really two cases, all right? Because the derivative of inverse hyperbolic cotangent is also 1 over 1 minus x squared. So, but there is, devil's in the details here. And basically the story is the range of hyperbolic tangent turns out to be -1 to 1. Whereas the range of the hyperbolic cotangent is everything else. So between the both of them, we cover almost all the reals, except for, of course, the place where the denominator is 0, where it's singular, where the integrand is singular, namely at plus or minus 1. So just to complete the story here, this is for the absolute value of x less than 1. This is for the absolute value of x greater than 1. And for absolute value of x equal to 1, you shouldn't try to do the integral because that function's not defined there, right? Okay. But we'll do something kind of like that with this improper integration that we study later this semester, but one thing at a time. Now there are also derivatives of inverse hyperbolic secant, inverse cosecant, inverse hyperbolic cosecant, and those end up giving you things like x times square root. And perhaps we'll talk about those later. I almost certainly wouldn't. Well, I don't know. Maybe I'm not sure I'd get to them in calculus 1. It would depend on the class. So, but these things, perhaps you've seen, perhaps you haven't. But you should know about them. I hope you know about them now. All right. So I will start again here in a second.